Okay, we are on to QOD number 31, and I've started throwing in title slides now. So we're still in chapter 14. We're still talking about kinetics, and today we're going to talk about what are known as integrated rate laws. And these have to do with the relationship between concentration of reactants and time. Now, before we go on to that, I just want to do a quick review of where we have been so far in chapter 14 in kinetics. And I would say there's sort of three main ideas, and we're heading into the third one now. The first one is what I would consider sort of fundamentals of kinetics, and we took a look at all these things in the lab that we did with the Time's Up lab that we did with the iodine clock reaction. And so some of the fundamentals of kinetics that we learned were that as a reaction progresses, the reactant concentrations decrease. So over the course of time, reactant concentrations decrease. And that product concentrations increase with time. So as reactants are being consumed, products are appearing, and that the reaction slows down as it progresses. And so it's not a straight line when we graph reactant concentration versus time or product concentration versus time, but it's a curved line and it's got a steeper slope near the beginning, and then it begins to level out. And then that rates of appearance and disappearance are related by the coefficients in the balanced equation. That was sort of the first thing we talked about. The second the second big idea I would talk about would be the relationship between concentration and rate. And this is the most recent thing we've been doing with rate laws. The reaction rate is a function of reactant concentrations, and we can describe these by a rate law. And then, but the other thing we learned was that the rate law exponents are not obvious from the balanced equation, and they have to be determined experimentally. And so if we have data for initial concentration of all reactants and initial rate, then we can work out a rate law. And we can also, with the exponents of the reactants, and we can also work out a value for K. Well, that takes us to what I would consider to be the third big idea of kinetics, which is the relationship between concentration and time, and that's what this video is going to be about. And so here's some ifs. If we know the rate law, and we figured out how to do that, and if we know the value of K, and we figured out how to do that, and if we know the initial concentrations of the reactants, and that's an easy thing to work out, then if we know those three things, then we can calculate the reactant concentrations at any point in time during the reaction. Now, here's the thing. This requires calculus, and it's not particularly easy to do this for reactions in which there is more than one reactant, which unfortunately makes up the vast majority of reactions that we're interested in. However, we can do it in a fairly straightforward way for reactions in which there is only one reactant. And so everything we're going to talk about today is based on the special case of reactions in which there is only one reactant. That is, A goes to products. And so there are really only two types of reactions that are possible here. Either a decomposition reaction in which three types actually. Decomposition reaction in which A goes to multiple products, or a combination reaction in which two or three molecules of A combine into a more complex molecule. The third type would be an isomerization reaction in which one molecule of A just simply changes its structure but maintains the same formula so that it forms an isomer of A. And so we have that specific case in which there's only one reactant. The other thing is there's really only two possibilities when you have one reactant, and that is that it is either a first order reaction or a second order reaction. It's really not possible to have a reaction in which you have a single reactant and it's zero order. I'm not aware of any examples of that. And then I'm not really also aware of any examples of any time where you have a single reactant and it's third order or fourth order in that reactant. And so there's really two, if we're limiting ourselves to only one reactant, then there's really two possibilities. that it's first order in that reactant or it's second. So let's take a look at what we call the first order integrated rate law. And this would be a particular example in which I have a single reactant going to products and the reaction is first order in that reaction. That is, rate is equal to K times the concentration of A raised to the power of 1, which is simply K times the concentration of A. I can rewrite this. Rate, remember, is the change in concentration with time. So at any point along that curve, we talked about this actually on the first day of talking about kinetics. We can determine the instantaneous rate at any point along the curve using calculus by simply taking the derivative of the line at that point, which would be dA dt. Is equal to negative Ka. Why negative? Because reactants are rate is always expressed as a positive number, but the change in reactant concentration is always a negative number. So we had to put a negative in front of this to get a positive rate. So I've simply put the negative over on this side. I could further rearrange this again. I'm not going to write this equation, but I could write it as dA equals negative Ka dt. And then I'm going to integrate that over from t equals 0 to t equals infinity to go from finding the slope at any particular point to doing the reverse, which is knowing this information and being able to work out the relationship between concentration and time. And when I do that integration, you don't need to know how to do this in calculus, I get this equation. That is the natural log. Here's something you need to get used to seeing. Natural log, which is ln, of a at times t over a at times 0 is equal to negative kt. So in other words, a a0 is the initial concentration of A, and A subscript T is the concentration of A at some time T over the course of the reaction. Now I'm going to take this same equation and I'm going to do some algebraic manipulation of it. You may recall from algebra that if you have the log of a product, that is the log of A times B, is the same as the log of A plus the log of B. And you may recall that the log of a quotient, the log of A divided by B, is the same as the log of A minus the log of B. So I'm going to do that here. The log of A over B is equal to the log of A minus the log of B. So this term is exactly the same as this term. So that is just simply using some logarithm principles that you learned in algebra. Now I'm going to add the log of A 0 to both sides. That gives me this equation. Log of A at t is equal to negative kt plus the log of A at 0. Well, why are we interested in that? Because that is now an equation in the form of y equals mx plus b, which is a linear equation. So in other words, we can graph it for any first order reaction. We can graph concentration versus the log of concentration versus time, and get a straight line whose slope is equal to negative k and whose y-intercept is equal to the log of the initial concentration. So here we're just saying that again. I'm taking this equation and saying that if I collect data for a first order reaction in which there is only one reactant and plot the log of concentration versus time, I will get a straight line and the slope of that line will be negative k. So let's take an example, and here is an example of an isomerization reaction. The formulas, the chemical formulas of the reactant and the product are the same, C2H3N. One of them is called methyl isonitrile, in which the CH3 is attached to nitrogen, which is attached to carbon, CH3NC. The product is acetonitrile, in which the CH3 is now attached to the carbon, which is attached to the nitrogen, CH3CN. What simply happened is that these two atoms have reversed position. And this turns out to be first order with respect to methyl isonitrile. And so if I take some methyl isonitrile and heat it up to 200 degrees Celsius, that is 473 kelvins, I will get this reaction beginning to occur. And I can simply take a series of data points of, pressure versus time. This is a gaseous reaction, so it's easier to measure pressure than it is to measure concentration. But as long as I've got a fixed volume, then pressure is simply going to be proportional to concentration. And so pressure, we can simply use pressure the same way we would use concentration. I can graph pressure versus time, and this is what you would expect to see for a reaction, that the pressure of the partial pressure of the reactant is going down over time, but it's not a linear thing. As the reaction progresses, dependent on concentration, and so the rate's going to go down. That's a reasonable sort of graph that we would expect to see, and we've seen things like this before. Here's where the first order integrated rate law now kicks in, because if I take those very same data in which I've graphed pressure versus time and instead graph the log of pressure versus time, I get a straight line. And furthermore, going back to that equation we saw a couple slides earlier, the slope of that line is going to be equal to negative k. So I can very simply, fairly easily work out the slope of that line. It's equal to negative 5.1 times 10 to the minus fifth reciprocal seconds. And therefore, k is going to be equal 5.1 times 10 to the negative fifth reciprocal second. Let's just think for a second about units. This is a logarithmic function, therefore it's unitless. The x-axis is in seconds, and therefore unitless over seconds gives us reciprocal seconds, which is what we know is the units of k for a first order reaction. All right, we're going to keep moving, and we're going to talk about a second order integrated rate law. Remember, for a second order reaction, just the simple rate law is equal to rate equals k times the concentration of A squared. Oh, so let me just go back and say all the way back to here and just say this. This equation fulfills the requirements that I was talking about earlier, which is if we know the rate law, and we do, it's this, okay? If we know the rate law, and we know the value of k, and we know the initial concentration, then anywhere along the line, we can work out what the concentration of the reactant is going to be at any time. So if we know the rate law, and we know the initial concentration, and we know the value of k, if you give me the time, I can calculate the concentration of A at that time. If you give me a concentration of A after some unspecified period of time has passed, I can tell you what that period of time is. Now we're going to do the same thing for second order. Okay, the rate law is this. Once again, I can rewrite that. Rate is equal to dA over dt, and furthermore, I could rearrange this one more time to say that dA is equal to negative k a squared dt. I'm going to integrate that over t equals 0 to t equals infinity. And when I do, I get this equation, that 1 over the concentration at time t minus 1 over the concentration at time 0 is equal to kt, where once again, A subscript 0 is equal to the initial concentration. A subscript t is the concentration at some time t, and t, of course, is the time that has elapsed to get me to this concentration. Well, once again, I can do some algebraic manipulations of this equation, and that is I can add 1 over A0 to both sides. That gives me this equation. And once again, why is it I'm trying to get to this equation? Because this is a linear equation in the form of y equals mx plus b. And so therefore, if I have a reaction in which a single reactant goes to products, and I know that it is second order in A, then if I plot reciprocal concentration versus time, I'm going to get a straight line. The slope of that line is going to be equal to k. and the y-intercept of that line is going to be equal to the 1 over the initial concentration. So let's take a look at an example of this. Now, we know this is going to be second order because we're talking about second order, but let's just pretend that we didn't. Here's a reaction. If you take nitrogen dioxide and you heat it up, now not to 200 degrees like the previous reaction, but 300 degrees, so this is 573 Kelvin, it will start to decompose to form nitrogen monoxide and oxygen gas. And if I do this reaction and measure the change in concentration with time, I will find that if I start with 0.01 molar nitrogen dioxide, that after 50 seconds, it's gone down to this value. After 100 seconds, it's gone down to this value, etc. Okay, now let's say I don't know what order this reaction is. So the first thing I'm going to do is I'm simply going to check to see if it's a first order reaction. And I do that by taking the log of each of these values. This column is now not concentration after time, but the log of concentration after time. And now I'm going to plot those values, and I'm going to get a plot that looks like this. And unlike what we saw with the first order reaction with methyl isonitrile, this is not a linear function. This is a curve. It's not linear. There's not a equation that describes this, a straight line equation that describes this. And therefore, this is not a first order reaction. So now I'm going to check it to see if it's a second order reaction. Instead of taking the log of concentration, I'm going to take reciprocal concentration. And I'm going to plot that versus time. So I'm going to graph reciprocal concentration versus time. And now I see that I get a straight line function. And based on our original equation, if I'm graphing reciprocal concentration versus time, the slope, m, is equal to k. The y-intercept is equal to 1 over the initial concentration, and I get a linear function. Okay, let's keep moving. And the next thing we want to talk about is half-life. And half-life, to the extent that you're familiar with the concept of half-life, you've probably heard it from radioactive decay, which is where when I think of half-life, what immediately often comes to mind is radioactive decay. Well, this is an isotope of uranium whose half-life is equal to 13 billion years or something like that. But half-life is defined as the time necessary for 1/2 of the initial amount of reactant to react. So here, once again, is the methyl isonitrile reaction. I'm starting with a partial pressure of 150 torr. 1 half-life would be the amount of time it takes for this to go down from 150 torr to 75 torr, which means half of the material is gone. Now another half-life is the time it takes for it to go down from 75 torr to 37.5 torr, because now half of what I had here is gone at this point. After another half-life, it would have gone down from 37.5 to 18.75. That would be another half-life. Now, here's an important thing to note when it comes to working out relationships between half-life and K for these integrated rate laws. Because at the half-life, which we abbreviate as T1/2, because at T1/2, the concentration of A is now equal to 1/2 the original concentration, we can simply say this: when T is equal to T1/2, then the concentration of A is equal to 0.5 times the original concentration of A. That's the definition of half-life, time at which the concentration is now 1/2 of its original value. Well, we can work out a relationship between half-life and K for a first-order reaction simply by going back to the integrated rate law for a first-order reaction and substituting those two things in. When T is equal to T1/2, then A is equal to 1/2 of the original concentration. Well, now I can cancel those two terms out because I've got the same term on the top and the bottom. That tells me the log of 1/2 is equal to negative K T1/2. The log of 1/2 is equal to negative 0.693. And therefore, if I divide both sides of this equation by negative K, that tells me that T1/2, the half-life for any first order reaction in which there's a single reactant, that the half-life is equal to 0.693 over the rate constant. The other way around is the rate constant is equal to 0.693 over the half-life. The key thing to notice here, and this actually is, to the extent, again, that you've thought about half-life, this is just sort of intuitively consistent with what you would think. Half-life is a constant. It doesn't change. It is simply inversely proportional to the rate constant. And if I know the rate constant, then I can calculate the half-life, and it is also a constant. By contrast, if I know some radioisotope and I know its half-life, I can calculate its rate constant, and that is going to be a constant. Well, let's look at the second order integrated rate law. This, once again, is the second order integrated rate law in its linear form. I'm once again going to substitute in those two things. When T is equal to T1/2, then the concentration of A is equal to 1/2 the original concentration of A. Now I want to do some algebraic manipulations here, and so I need to get these two fractions to have the same denominator. So I'm going to take this fraction and multiply top and bottom by 2. That gives me this. Now because these two fractions have the same denominator, I can group them and subtract. So 2 over A0 minus 1 over A0 equals KT. 2 minus 1 over A0 is 1 over A0. Now I divide both sides by K, and I get 1 over K A0 is equal to the half-life. Now this is just a little bit strange when it comes to sort of intuitive understandings of these things, because I always think of half-life as being a constant, but that's really only true for a first order reaction. It turns out for a second order reaction that the first half-life is going to be shorter than the second half-life, and the second half-life is going to be shorter than the third half-life, because as the concentration of A goes down, the half-life is going to get longer. In other words, A0 for the second half-life now resets to whatever A is at that point, and it just keeps getting longer and longer and longer. Well, we've said a lot and we've used a lot of time, and so I just want to go back to what the key takeaways from this video are, and really what you can expect on a QOD. And of course, we'll spend time in class talking about the actual math and doing some examples. But the first thing I wanted to show you is simply the section of the AP Chem formula sheet that deals with kinetics, and what they give you on that formula sheet is the integrated rate law for a first order reaction. There are various ways of expressing this, but this is the integrated rate law for a first order reaction in which there's only one reactant. Here's the integrated rate law for a second order reaction in which there's only one reactant. And here is the half-life expression for a first order reaction. And then they define that K is equal to the rate constant, T is equal to time, and T1/2 is equal to half-life. So what are the key takeaways? How could I summarize this entire video? For a first order reaction, and one more time, let me specify that we're talking about we're talking about reactions, the special case in which there is only one reactant, only one species is the reactant. For a first order reaction, plotting the log of concentration versus time gives a straight line whose slope is equal to -K. And half-life is a constant that is inversely proportional to K. For a second order reaction, plotting reciprocal concentration versus time gives a straight line whose slope is equal to K. And half-life is not constant, it's dependent on the concentration of A. But it's also reciprocally related to K. So I will have given some suggested problems along with this video posted in Veracross, but the QOD will largely revolve around these principles that we've talked about in this video. And thanks so much for watching.